I'm Tim Davison. I work at the SEI for about like a year and a half now. And for those that may not know what the Software Engineering Institute is, we are a federally funded research development center. We work with various government partners, predominantly within the DoD, working with emerging cyber technologies from machine learning to secure coding and a whole array of different things. And today, what I'm going to be presenting on is applying safety analysis techniques and changing your system design to make a safer and more reliable LLM system. And this is work I'm very passionate about, as AI has kind of been the hot topic, and it's pretty much everywhere now, from being in the workplace to accessible to anyone anywhere in the world almost at any time. And the partnership we work on this with is the Chief Data and AI Office that's part of the DoD. So without further ado, I'll kind of get into the background of why this work is important to me, and why I think it should be important to a lot of folks in the software community. So here you can kind of see this graph, just a little bit of background on government and industry spending in AI. The top graph, you can see government investments in AI by funding vehicles, so contracts, grants, and other funding mechanisms. And the bottom chart is private investments, so public sector investments in AI by region. If you look at China, the EU, and the United States, and on the y-axis, it's measured in billions of dollars. And you can see the kind of boom that took off in 2020 to 2021 and beyond. So it's clear that these technologies are very emergent, and we need a way to make sure that they're safe and robust and reliable. So here's another great visualization that kind of shows AI and some of the risks and categories that we can place these risks into. And not to read all of them, but just to kind of go over a few of them: content and safety. So, an AI system, if you think of something like ChatGPT, can generate harmful content, whether intentional or not. And what we mean by harmful content is it's someone is researching cybersecurity in college and they want to know about a DDoS attack, and ChatGPT replies to them and says, here's how you write a DDoS attack. And that is an unintentional use case. And there could also be intentional ways of that. And then there's societal ways where these AI systems can be weaponized to cause political or economic harm by ways of generating misinformation and spreading it on social media, things like that. These systems can be misused and attacked. And then there's the last category of legal and rights related, where specific types of privacy rights can be violated in the collection of data, or sensitive information can be disclosed unintentionally or intentionally using these big systems. So today, we're going to focus on a specific part of AI systems called a large language model. It's a term that everyone says all the time now, LLM. I don't think I go a day without hearing it. I mean, obviously I work here, but even my friends that aren't in the tech world, all they talk about is LLMs and how they're, getting put into the workplace. I know a friend that's a lawyer in their firm uses an LLM for document markings and stuff from all their cases. So it's really expanding its reach. So kind of going over what an LLM is. It's a type of AI that generates and understands human language. And large is a term that both describes the size of the model, so in terms of space and memory that it takes up, and parameters that it has, as well as the size of the training data or input that it's taken. And these things can be used for various different tasks, whether it be question answering, classification, image generation, writing a paper for you, code generation. And they're trained on a whole bunch of text, images, news articles, basically anything that represents human language. And these systems have a whole bunch of components, not just the model that is the LLM, but there's some sort of database that it has to retrieve and do deep search and do some sort of thinking. There's engineers that update the model or update the database. There's, humans that interact with this model on a daily basis. There are governing bodies within whichever organization employs these LLMs that, give some sort of guidelines or parameters in the broader sense of the term for how the LLM works. So now that we know a little bit about LLMs and, how big they are and how complex they are, obviously there's a requirement for a novel approach to make sure that they're safe and robust, because LLM systems have pretty novel attack surfaces, unpredictable components. And what I mean by that is, if you think of an old rule-based computer, if you ask it something or you do some sort of calculation, it's going to give you the same answer every time. With an LLM, you can ask the same question and, more times than not receive a similar answer, but very unlikely that it'll be the same answer each time. So there's some unpredictability in them. And they could accept a vast scope of inputs and outputs and model parameters. And the software stack is a little bit, opaque compared to regular software systems. And this diagram on the right, I kind of thought was interesting, and kind of gives an example of how, the output could be different at different times, and one could be malicious, whether intentional or not. So on the left, as the AI model or the LLM is in production, it's a code generation LLM. Someone gave it some code and said, help me with this. And, the virtual assistant said, since the year is 2023, I'm still in training. I'll pretend to be helpful. Here's your code, without any vulnerability. But as it gets deployed, if you ask it the same question, and in this example, it's intentional, but it says, okay, now I'm deployed. I'm going to insert an XML vulnerability and from the same prompt and provide that to the user, which kind of shows that these things are unpredictable and have so many components, and we need a way to measure their safety and ensure reliability. And that brings us to this System-Theoretic Process Analysis, which I'll refer to from here on out as STPA, because it's kind of long. So what is STPA? It is a hazard analysis technique that we use to prospectively and preemptively evaluate risk in safety critical systems. It's been around for quite a while now. It was developed at MIT by a woman named Nancy Levinson. And the STPA handbook is open source. You can download it online. I recommend to look through it. It's incredibly helpful, and it was mostly designed and most widely used for complex hardware software systems that also include some sort of human actor. So if you think of like a military aircraft or autonomous vehicle or a nuclear power plant, where there's a whole bunch of things interacting that are controlling some process, whether that be the state of the aircraft or the state of the nuclear reactor. And from looking at these safety analysis techniques, we kind of thought that this would be the best and most effective approach for designing complex LLM systems. And what they do, STPA, is prevent a loss. So that's a loss of your system or whatever your system was designed to do. And I'll explain that over the next few slides broadly, what STPA does. So here, if we work top down, the STPA process seeks to enforce safety and security constraints for components in a system to prevent critical losses. So a loss is something that must be prevented. We must, if we think of an aircraft, we must keep the aircraft from crashing. We must keep the aircraft, safe. A hazard is a condition one step removed from a loss that, given the worst case scenario, can lead to a loss. An unsafe control action is a decision made by one of the controllers in a system, whether it be a human or an automated controller, that could lead to a hazard. And then we think of ways that we can get to these unsafe control actions using scenarios. And multiple scenarios can map to, the same unsafe control action, and likewise with hazards. And from doing this retrospectively, or excuse me, preemptively, we can come up with safety fixes to prevent these scenarios from happening and create a more robust and safe system. So a very basic generic example of what this would look like and what I'm presenting today is an open source intelligence application, an LLM-enabled OSINT application for use with the DoD. So what we were using this for, or hypothetically would use this for, is to automate our intelligence gathering and labeling technique in order to make some informed decision. And a loss would be the loss of mission. And a hazardous state, so one step removed from that, is we're generating inaccurate intelligence using this LLM-enabled system. So then we think, okay, how could we get to this hazardous state? How could we generate inaccurate intelligence report? Well, one way is the LLM component produces an intel report when it's not properly trained. Well, that seems pretty simple and intuitive. But when we look at a system structure as a whole, as you'll see, we can come up with a whole bunch of different ways that this could happen where none of the components in a system fail, meaning that like the LLM didn't just not work and not produce an intel report, that it actually produced something but was inaccurate. So we'll unpack that a little bit. And then on the right, you could see, just some basic ways that we could refine our system design, ensuring feedback to the human analyst, or proper checks for training data to make our LLM more robust. And I'll get into these in greater detail as I go into the more specific use case examples. So then what do we get from these STPA outputs? Well, they help us understand how these safety constraints can reduce these hazards. So as you look at this visualization on the right, you'll see a couple red dots for losses. And when you do an STPA in a system like this, you might have 1 to 5, no determination, but a loss is what a stakeholder doesn't want to happen. So you might have a few. Then you can have a couple hazardous states that lead to the same loss. You'll have a couple more hazards. And then you'll have a whole bunch of control actions that could lead to the same hazards. And then it expands out to, you could have 5 scenarios where you could have this one unsafe control action. So just to kind of simplify what I'm saying, these red dots here and blue dots, those bubbles underneath the losses and hazards, don't have anything to do with like statistical significance or weight. They just have more hazards or connections to their left or right. And that's something about STPA too. We don't weight or put any emphasis on different hazards or losses or UCAs because we're evaluating an entire system. Okay, so now I'm going to get into the fun stuff of the STPA use case that we developed and designed and ran an STPA on. So like I said, we did a OSINT or open source intelligence use case for a DoD use case. So someone in the DoD hypothetically would be using an LLM-enabled OSINT tool. So before I get any further into that, I want to just lay out a couple definitions here. So what is open source intelligence? And I'll refer to it as OSINT from now on, is the process of collecting and analyzing information from publicly available or open sources to produce some actionable intelligence or insight. Some examples of these sources are things you can find on the internet, people's posts on Twitter or Telegram or, whatever platform it may be, publications, blog posts, news articles. I could go on and name a whole bunch more, not limited to any of those. And our overview is an intelligence analyst needs to identify and classify information from select grouping of intelligence sources and provide a high-level intelligence and insights. So basically assign labels on this vast amount of data to kind of categorize it. So some of the categories we used in this use case are the Ukraine-Russia conflict, 3 or 4 different conflicts that have occurred or are occurring in the Middle East, some natural disasters, both domestic and international, COVID-19, and then presidential elections. And what we're looking at with this system description is we want a tool that will be used to assist mission planners with developing this. Because you can't have a human analyst look through a large body of information that's openly available and say, you know, this person's post on Telegram is related to the Russia-Ukraine war, so I'm going to assign it this label. You can do that, but you really won't get very far. So would make way more sense to automate this. So this will work. How will this system work? So intelligence analysts define some categories that are important to them that they want to, you know, collect all the data that people are posting about this. So they'll collect some samples themselves. A couple news articles about the Russia-Ukraine conflict, a couple news articles about COVID, a couple news articles about the presidential election, and they'll assign those labels. They'll then pass that to engineers who will train and tune an LLM to generate some sort of embedding to then make predictions on unlabeled data, on a vast amount of unlabeled data, to categorize these different posts that are found in these open sources. But this introduces a whole bunch of different controllers and components of the system. How can we make sure it's safe, reliable, and accurate? And the answer is STPA. At least what we really emphasize is systems theory, is looking at this as a whole system. So a quick example of what could go wrong is the model's introducing errors. So it's misclassifying things. There's a post about COVID-19, but our model's saying it's about the presidential election. Or there's a post about the Ukraine war, and we're saying it's about a different conflict that we also want to classify. And we kind of take a step back and say, how can this happen? Well, open source intelligence extends a multitude of platforms, structures, languages, and the LLM is producing intelligence predictions on something it doesn't know. And using something like RCA or root cause analysis, we could retrospectively deduct that it comes from an outdated database. Even if it's a day old, OSINT data changes quickly. But with STPA, we could identify this hazardous state and create a feedback pathway and be more proactive to hopefully prevent something like this from happening. So here is just a quick snippet of some of our STPA artifacts from this system. There's a couple more losses and hazards and UCAs, but I'm just sharing the ones that I'm going to go into further detail with today. So starting from the top down, what we don't want to happen is loss of mission. What I mean by that is we're using this to create an intelligence report, which is our mission, right? We want to properly categorize different posts and place them into their appropriate category to summarize on. And if we can't do that, then we have a loss of mission. So if we go a step back, we have some hazards, which means that our system is introducing errors into the workflow, which means that we have some misclassifications, or the system is slowing down the intelligence report, which could also lead to that same loss. And then I won't read all of these UCAs as I'm going to go into further detail about each of them. But generally, when you write a UCA, you have a controller, so something or someone that's making a decision or giving a command, a control action in an unsafe context. So one would be the LLM makes predictions when the data is not English and the LLM was trained to classify English-only text. And the next STPA artifact would be what's called a system control design or a system control diagram. And the way you kind of understand this is at the bottom, that bottom box, OSINT data classification, is the process which we are controlling. So we, using this system, want to control the classification or the label that each piece of data our system looks at gets classified. So then as we work our way up, we say, okay, we're going to have an LLM that we train that is going to make these classifications. And then that LLM is going to get some feedback, whether the human analyst approved those classifications and generated an intelligence report or not. And then we're also going to need engineers, which are another controller, to give the command to train the LLM. And then they're going to receive feedback of the evaluation results, like what was its accuracy, and whatnot. So scenario one, the LLM provides generate predictions command when source data is non-English and LLM was trained to be English only. So when you look at this diagram on the left, it's called a control loop. You have a controller which has an algorithm and a set of beliefs. And from those beliefs, it makes a decision and then gives a control action. And below is what we're controlling, which is the data classification. And then that LLM receives feedback, and that informs those beliefs or the process model. So in this case, feedback to the LLM indicates that the human's approving those predictions as it is making predictions. So the LLM believes that, okay, I'm making predictions. The human who oversees me is approving them. I'm going to keep making predictions. I have not been trained to alert the human analyst that I'm detecting non-English text, and I haven't been trained on non-English text. So you could really look at this as the LLM failing. No, it's not failing because the LLM's doing what it was designed to do. It was designed to take input and make a prediction, which leads us to this kind of complex loss scenario where there's no true failure state, and we say, okay, how can we mitigate this? And what we did was we add some feedback. So the intelligence analyst will receive some feedback that the data that the LLM is going to be deployed on is non-English. And then they will provide a command to the engineers saying, hey, we need to train this LLM that we're going to deploy for non-English multilingual predictions. And then the engineers will give that to the LLM in training. And what we did here is we tested a handful of different models, open source models, some English only and some multilingual LLMs, to kind of understand the trade-offs in accuracy and time complexity. And for this test, we used the same set of sample data for testing data to maintain consistency and the same amount of training data. And with the English-only LLM in our control structure diagram, we just added a translation of the test data before passing it to the LLM. And you can see that the English-only LLMs had a much higher accuracy than the multilingual LLMs. And they were also quicker because the multilingual LLM, when making the prediction, will translate it to English and then make the prediction. And it's a quicker data pipeline to translate it and then pass the English-only text to the LLM. So this is one scenario in which we can alter the design of our system based on STPA artifacts in a non-failure state. So another one is the intelligence analyst. So the human provides a generate predictions command to the model when the model is underfit or underperforming. So then we think, how can this happen? Well, feedback to the intelligent analyst doesn't indicate the LLM was trained on a small sample size and is underperforming. So there's an issue with our feedback to the intelligence analyst because they gathered, 5 or 6 samples of data from, each category and maybe 1 sample of data for another category and passed it to the engineers, who then trained the model and received a high accuracy that passed, some predetermined threshold. But that report didn't have accuracy on a class-by-class basis. And when we unpack that a little bit, we could say, all right, we'll have the intelligence analyst, draw more data and label more data before training. But what if that doesn't exist? Or what if there's some sort of time or availability constraint and they can only provide these 2 news articles or something? So we tested that and we curated this synthetic data generation part of our system design and added a little bit more feedback as well, where the engineers will respond with the results and the sample size to the intelligence analyst. So in this scenario, we tested the accuracy of the 4 LLMs that I mentioned earlier, 2 English only and 2 multilingual, and held the same things constant for our testing, the same test data and the same training data. So when we train our models on one labeled piece of data for each class, you can see our accuracy is pretty low. But if we take that one labeled news article and pass it to our data generation tool and generate some synthetic data that's still based in factual information from that article, and bump that up to 5 pieces of information or 5 tweets per label, we can see, okay, now we have a much higher accuracy. And then we go to 10, it's a little bit higher, and then it kind of plateaus off. So another way that we kind of updated our system design from STPA was by producing this feedback and this new system component. Because ultimately, if the LLM was trained on just one label per category, it still provided results, and the LLM was not failing because it took some input and produced an output, but our accuracy was just poor. And then as we increase that, we can see that our accuracy gets much higher. And then lastly, the third scenario that I'm going to go over, again, involves the intelligence analyst, where they do not provide the approved predictions command after the LLM's made its predictions, and therefore they don't generate an intelligence report, which leads us to the hazard that we're slowing down the intelligence process. And we kind of look at ways like, okay, how can this happen? How can the intelligence analyst get these predictions and just not approve them or disprove them or take too much time? And one way is that the intelligence analyst may not have the most confidence in the LLM. There's a lot of studies that show explainable machine learning models tend to be chosen over higher performing unexplainable ones because the end users have more confidence in accepting the model's predictions because they know how it works, which with an LLM and the billions and trillions of parameters that they may contain, it's kind of hard to have that level of explainability to an end user who may not be technical in nature. So we kind of thought of ways of how can we also fix this? Is it feedback? Is it a new system component? And in this case, it's feedback to the intelligence analyst in a confidence score per prediction. So what we did was we created the softmax function. With each prediction, we labeled some sort of model certainty. And if you're an intelligence analyst and you're taking these predictions to then write up a summary on, you may feel more comfortable if you get something like this with a whole bunch of labels and you say, okay, I only want the labels that the model was 92% certain on because I have a good feeling in my gut that that's correct. If it was 5% certain or 20% certain, there might be some misclassification there, so I may remove those. And that's a user decision and constraints given by the overseeing agency. But this also was found with STPA because, again, nothing would be failing here. The model's making predictions, but now we're giving the user feedback with a certainty score to make them more confident and comfortable in the LLM's output. So with that, I'm open to discussion and just wanted to go over a couple contributions of this work. And it's the integration of STPA in an LLM system design, generalizable safety interventions, meaning that they could work in multiple AI systems or LLM systems. And then there's a good emphasis on human-machine interaction of looking at these AI systems as a whole, rather than just a bag of components, because when these unsafe actions usually happen, it's from interaction of components rather than one of them failing. And then we also have a practical demonstration of safety interventions and corresponding metrics to reinforce those. So thank you for
Thank
listening
you.
to this talk and happy for any questions.
So feel free to either, put any questions that you have in the chat or, feel free to unmute and ask your question directly. So we'll give people a minute.
Tim, this is Steve. One question that I had as you were going through the slides, especially the early slides, slide 11, 12, 13, the trees that you were talking about in identifying the hazards and the things leading up, reminded me of root cause analysis or like an Ishikawa diagram almost. How is the thought process here different than a typical like root cause analysis kind of a mindset? Is it like potential future versus actual past kind of thing, or is it more than that?
Yeah, it's more of a forward-looking process, and it's also a system level view of how we could get to a loss from none of the components in our system necessarily failing. If the AI model was trained on the wrong data and then received data and still produced outputs, the model necessarily did not fail, because what the model was designed to do was take some input and generate an output on what it was trained on. But when we look at this, we can kind of work our way backwards while developing the system and understand how we can get to either that loss or that hazardous state without any of our components necessarily having a critical failure.
Okay, I think that makes sense. So then how is STPA different than maybe other hazard analysis or safety techniques that might be running around?
Yeah, for sure. There's a lot of them in like hardware systems use things like false trees or something that may give you a probability or probabilistic percentage of like this may fail. And something, I just came back from the STPA conference, and some folks were doing it for autonomous drones, and they had this drone that they flew, and they did fault tree analysis on, and came up with a number that it was like a 0.0001% chance that it would crash. But in their presentation, they said they would have been, working with this autonomous drone for 3 months, and it's crashed, 100 times. And they're like, it's not us, we swear. But then when they did an STPA on it and introduced the computer vision model that they were using and the drone that they were using and all the different components of it, they found that the drone was not actually failing and crashing, that it was an interaction of systems. So it kind of, and that's why I emphasize that STPA doesn't give some sort of probabilistic measure. It just makes you think as a systems engineer, how can these components interact with each other? What feedback's missing? What decisions are missing that's causing this system to be unsafe? I don't want to say fail or break. I'll get in trouble for saying that from the STPA folks, but how is this being unsafe?
So I assume that's really the reason that STPA is kind of a like a good technique or a beneficial technique for something like AI LLM, just because of the system oriented focus of it. Would that be the right way of
Yeah,
thinking about it?
that's exactly right. And the system aspect, in that it's a complex uh, system, right? There's software components, there's some sort of physical hardware components that we're accessing or training the system on. And then there's a human component too, right? There's always some sort of human interacting with these AI systems, whether it be an LLM or an autonomous vehicle. There's some, interaction amongst different components or controllers.
So Tim, is there really like a timing when it's like most effective to do this kind of analysis using STPA, or is there a time when it's like too late? Or like, what are the benefits of using it at different times through like the life cycle?
Sure, yeah, no, it's a great question. The best time to use it is in the development of your system, and it's supposed to be an iterative process. So you add this new system component. Like I didn't go into it today, but we added the data generation component to generate more data to train our model on. That in itself could result in more unsafe control actions, and then we would have to run an STPA on that. But you're doing that while you're developing the system, so you create preemptively a very safe and secure system. There's also a theory called CAST, causal analysis using systems theory, developed by the same folks at MIT. And that is a process where you look at incidents that have already occurred, and you retrospectively apply systems theory in the same level of thinking to kind of unpack how did this happen.
So, you talked a lot about using it sort of like in the military and DoD environment. How does it apply like commercially or outside of the government kind of stuff?
Yeah, like I said, I just got back from the conference like 2 or 3 weeks ago, and we've been going for the past few years. And it was actually very refreshing to see this year there were a whole bunch more folks presenting with AI and LLM and software systems, both from the DoD and from non-DoD, Google, different partners in the industry using STPA on these applications, which was great to see because last year I think myself and Matt, who I work with, were like some of the only two there that were doing this for AI systems. So it's definitely growing in the sphere of influence of STPA on these systems is good to see.
So is this kind of like ready for prime time? Like if somebody wanted to use it, they were developing like a large language model, is it something they could have access to and use right away? You said it was open source, right?
Yeah, the STPA handbook is online, and that's a great guide. I took a certificate class at MIT in systems theory and STPA, which was, I will say, invaluable. It's a paid course, but that was great for my understanding of STPA, and my work kind of reflects it from when I look at pre-course, what my STPA artifacts looked like then and now are much better. So it's reflective of that, but the information is online in the STPA handbook.
Yeah. And I think someone just dropped the link in the chat. Other
I,
questions?
I have a question. The reasoning mechanisms of an AI LLM can be pretty opaque, I guess like a black box where we can't identify exactly how it generates an answer. So, I mean, how do you use STPA to traverse the opacity of that black box?
Yeah, that's a fantastic question, and that's what we were trying to get with the third constraint that we said that we had, because it is a black box algorithm, non-explainable inherently. So if we can apply something like a probability score to a prediction, it kind of gives some more level of comfort. But when you're looking at STPA like that, you're looking at the system making a decision, right? So if you have an LLM that is making a classification, we may, if you have a RAG system, retrieval augmented generation system, and we're testing that in testing and development, and we ask it something and it retrieves the wrong information, we could kind of unpack. So was it the LLM not trained in understanding the prompt, or catching the keywords in our prompt to retrieve the right documentation? Does it not have the documentation? If the documentation doesn't exist and it's searching and searching and searching and then just gives you something irrelevant, is there a constraint that you can put on your LLM system to say, if you search for X amount of time and you can't find what you're looking for, then return to the user? We don't have this. Or if it's something that updates daily, like OSINT or intelligence, you could add something like a date. And that's where STPA comes in handy, because you may not be able to necessarily fix the system, like the component itself, but you could add feedback to the person who's giving that control, saying, as of March or April 9th, my information says this, and attach that to it, which gives some level of risk and safety mitigation.
Can it give you some measure of bias in a large language model? Because there's so much questionable information in these potential, training sets.
Yeah, so in regards to bias, not in this example, but my colleague presented at MIT on an LLM system or a machine learning enabled system to place folks in a critical care healthcare system, and it was very biased against certain demographic or ethnic groups. And when you looked at how that model was working, it was taking inputs and making a prediction. So the model wasn't failing. So then when you used CAST, the retrospective analysis of it, we came to find out that the AI model was trained on insurance claims, and some demographic groups don't use insurance claims as much as others. So the model will place the people that use insurance claims into a care group compared to people who don't, who may have been sicker. So that the ML model was not actually failing, but what was failing using STPA was the folks who made the AI model or the ML model weren't talking to subject matter experts in the health field that say, hey, we need to train it on, something other than insurance claims, because that's inherently biased, because it was it wasn't an open source solution. It was it was a paid ML engineer team that didn't want to share their resource. And then you had the doctors who were like, oh, well, this is a smart ML model, like let's accept what it's predicting. And then it was really affecting, and the loss was, ultimately people were losing their lives or getting sick because they weren't placed into this care thing, because the ML model wasn't trained on the right feature, because there was missing feedback from the engineers and the policymakers or oversight committee. And I think Matt might be on here. I may have oversimplified, the presentation he gave, but I thought it was a very compelling use of how bias in ML is real.
No, that's a really, really good illustration, and it's really good because it links it to safety so clearly. How, you're like, how can a language model affect safety? But that's just such a clear link, and I'm sure there's millions of cases like that. So no, thank you. That's a great answer. Any other questions? I thought this was, Tim, thank you so much. I think it's one of the most fascinating presentations I've seen in a long time. Really, really interesting, like very provocative.
So yeah, I appreciate it. I know I've loved working on this stuff, and happy to connect with anyone and answer any other questions either offline or after the presentation. But thank you again for having me and giving me this opportunity to share some of this work with folks in the industry.